Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and this is part 3 of related rates. In the previous 2 videos, I talked about what related rate problems were like, the strategy that you use in order to solve the problems, and we looked at a number of examples. I saved the worst for the last. These are what I would consider the more challenging related rates questions, but they're ones that you're probably going to encounter. So let's take a look and see how we solve them. The first example says a tank in the shape of an inverted cone has a radius at the top of 1.25 meters and a height of 2.5 meters. Water is flowing into the tank at a rate of 1.5 cubic meters per minute. How fast is the level rising when it is 1.75 meters deep? So we're talking about the volume of a cone. So we need to know that formula first of all. And the volume of a cone is basically 1/3 the volume of a cylinder. So 1/3 pi r squared times height. We have a situation where we have volume is a function of 2 independent variables, radius and height. The problem is I know this rate of change and I want to know the other rate of change, but I don't have a rate of change for radius. So you may encounter situations where you do have 3 variables and you only have one rate of change and you're asked to find the other rate of change, which means you need to get rid of that other variable. So we need to find a way of writing that other variable in terms of the one variable we are going to keep. So in other words, I want to get rid of radius. I want to write it in terms of height. In order to do that in this example, I'm going to bring up a topic called similar triangles. 2 triangles are considered similar if all of their angles are equivalent. So I'm going to make this a right angle in both of them, and then that's just the notation for equal angles there, and then that's the notation for those 2 angles being equal. If you have 2 similar triangles, they don't have to be the same size, just the angles have to be the same, then there's a relationship between the ratio of the sides. And that ratio, for example here, A to B will be equivalent to the ratio in the other similar triangle, C to D. So that's something I can use in this particular example. I know that if I were to take a cross section here, split this down the center, I've got a right triangle where this is 1.25 meters and this is 2.5 meters. Again, I'm picking nice easy numbers in these examples just to try to make it as easy as I can. We do have calculators that can handle any numbers, but I think it's easier to see the relationship when I choose nice, neat numbers. And if I were to take, when the water's coming in, wherever that water is at that point, I'm going to have a radius here and a height that are both changing. So therefore, this is my height, this is my radius. I can use the fact that they're similar triangles and it will allow me to express radius in terms of height. So the ratio of radius to height will be equal to 1.25 to 2.5. So in other words, radius will equal 1.25 to 2.5 times height, and that's equal to 0.5 h. So the radius is always going to be half of the height based on similar triangles. That allows me to replace radius with 0.5 h, and then I've eliminated one of my variables. So I'm going to do that first before I do any differentiation. If you don't do it first, when you differentiate, we would have to use the product rule and we'd have to put our rate of change of radius, which we don't know. So you're going to get stuck. So we need to do it at the beginning. So it will be 0.5 h, and the whole thing is squared h. I'm going to clean this up. So 0.5 squared is 0.25 h squared. And then I can clean that up. It will be 0.25 pi over 3. I'll just keep the constant part together. H squared times h is h cubed. Now I have volume in terms of just one variable, which is going to work because I only have one time rate of change. Now that I have my function in terms of one variable, let's figure out what we know and what we need to find out. So it tells me that dV dt, water is flowing into the tank, so it's increasing, so it's positive, of 1.5 cubic meters per minute. It says how fast is the level rising, so find the change in height with respect to time when height is 1.75 meters. Now that I've got that sort of written down, now I'm going to go ahead and differentiate this function with respect to time. So dV dt will be equal to 0.25 pi divided by 3. I'm just going to keep the function parts, I'm just going to keep the constant part separate, and then I'm going to differentiate h cubed with respect to time. So that will be 3h squared dh dt. Let's cancel the 3 there. So dV dt will be equal to 0.25 pi h squared dh dt. I want to solve for dh dt, so I'm going to isolate it. You can put your values in there first and then solve for it. I like to just punch into my calculator once. So dh dt, I'm going to divide both sides by this. So I'm going to have dV dt divided by 0.25 pi h squared. And now I'll plug my values in that I'm given. So dV dt is 1.5. H is 1.75. And that answer will be 0.624. Height is measured in meters. Our time is per minute. So the height would be raising at 0.624 meters per minute. And that's going to change depending on the height. You know, it's going to rise, the water's going to rise faster at the bottom than it is at the top, because at the bottom it's over less area than at the top. Let's try one more. Okay, our next question says a swimming pool measures 15 meters long, 10 meters wide, and it's being filled at a rate of 0.75 cubic meters per minute. The shallow end is 1 meter deep, the deep end is 3 meters deep, and there's a constant slope between the shallow end and the deep end. How fast is the water rising when the depth of the water at the deep end is 1.5? So it won't even be up to where, to this point yet, at 1.5. So again, let's figure out what exactly it is we're working with. It's a different question. This is a different question than if I said, how fast is the water rising when the depth of water at the deep end is, let's say, 2.5, because then we're in the whole rectangular shape. But when it's rising at a height of 1.5 meters, it's below the rectangular part of the pool. We're dealing with the triangular part. So I'm just going to focus on the triangular part of the pool and forget about, you know, the part above it. So the water is rising in this triangular part. In order to express the volume of that water in the triangular part, we take the area of the triangle and we multiply by the width of the triangle, which is 10 meters. The area of a triangle is 1/2 the base times the height. So if this is height, this would be considered base. And the area of a triangle is 1/2 the base times the height times their 10. So we've got our two unknowns. We want to get rid of the base. We only want to know the rate of change of height. So we're going to use similar triangles again. We know that this length is 15 meters and this length is 2 meters. So if we take a section of that triangle, it'll be a similar triangle. Therefore, B to H will be equal to 15 to 2. Therefore, B will equal 15 divided by 2 is 7.5 times H. So we can replace B with 1/2 times 10 is 5. B is 7.5 H times H, and that simplifies to be 37.5 H squared. Now we have volume just in terms of the one variable we want. We know dV dt. We're putting water in at the rate of 0.75 cubic meters per minute. They said, how fast is the water rising? So we want to find dH dt when H is 1.5 meters. So we're going to differentiate the volume of that pool, which we've expressed now just in terms of height, with respect to time. So dV dt will equal 37.5 times 2 is 75 H times dH dt. Therefore, dH dt will be equal to dV dt divided by 75 times H. dH dt then will be equal to dV dt, which is 0.75, divided by 75 times H, which is 1.5, to get 0.007. H is measured in meters, and my time factor is per minute. So that's how the level of the water is rising when it's 1.5 meters deep. And that will change at different heights. And then once you get above the 2 meters, we use a different function. We use the volume of a rectangular solid then. So it is very challenging, but by covering it, I'm hoping that if you do encounter something similar, you'll now be able to tackle that. Try some of these questions on your own, and hopefully they become easier for you after seeing these examples. Take care, and we'll see you on the next video.